Hello, good evening all. Am I audible as well as visible?
Yes.
Yes, ma'am.
Okay. Okay, so I hope you have watched the lectures for the fifth week that were based on mostly the syntax and the CFG's CYK algorithm and inside outside probabilities. Did you go through the lectures?
Yes.
Okay, great. Then I'll be sharing my screen. We have a couple of questions to solve today, so that we can get to know how well we understand the concepts that have been discussed. So, my screen is visible. Please confirm.
Yes, ma'am.
Yes.
Okay,
Mm.
just a second. Let's wait for 2 minutes. Some people are still joining. Okay. Let's wait for 2 minutes, okay? Then we will start. Meanwhile, if you have any doubts from the previous runs, if are there any doubts in the previous assignments? Okay, no one is responding. Okay, so we start with today's discussion. So, this is the first question for today's lecture. We are given four different statements and we are to identify the false statement. So, the first case refers to the running time of CYK algorithm and it asks what is the time complexity of it. And the other two, they discuss some other properties of CFG, that is the context free grammar. So, please try this question and we will discuss it shortly in 2 minutes. It can be multiple option correct, and here we are to identify just the false statements. And it can be multiple option correct. Please give it a try. If you have gone through the lecture for fifth week, you will be able to answer this question. And please post your answers in the chat box. You have to solve it now only. Give it a try once. This is the first. So this is the first question. Please give it a try. We will discuss the correct answers also. But first, give it a try from your end. Put your answers in the chat box, okay? Whatever you are getting or whatever you think is the correct option for this question, put your answers in the chat box. So any answers? A and B. Any other options? I want all people to give it a try. Please give it a try, all of you. Okay, let us see for other people. Okay, Sandeep says A is true. I think B and C are false. Correct. A is the true statement and B and C are false. Let us see why. So here it says first statement, it mentions the worst case running time of CYK algorithm. That comes out to be order of n cube into G, where G is for the length of the or the size of the CNF grammar. That is the CNF stand for the Chomsky normal form. So what are the properties of CNF? Can anyone tell? What are the properties? Please unmute and answer. Let us
Two
be
non
as
two
interactive as
non-terminal
possible. Yes.
two non-terminals or just one terminal?
Two. What did you say? Two.
Two non-terminals or just one terminal?
Yes. So given any production A, it can give me two non-terminals. This B is a non-terminal and C is a non-terminal. Or A can have the production rule of this form as well. So only these types of the productions are allowed. On the LHS, we will always be having a non-terminal, and on the RHS, we have either two non-terminals or a single terminal. This is your CNF, that is the Chomsky normal form. So it says the second case says like if the context free grammar it is in CNF, then G is always unambiguous. So this statement is false. Why? Because given any grammar, like let's say any CFG you have, if you have converted it into CNF, that does not guarantee that the grammar will be unambiguous. This does not guarantee. Why? Because ambiguity means, what does ambiguity refer to? Why? When can we say a CFG is ambiguous? Can
Yeah,
anyone tell?
CFG is ambiguous if there are multiple parse trees that can be
Yes,
created.
absolutely correct. So the property or the definition of the ambiguity of the grammar is if we have more than one derivation tree to derive a particular string, to derive one string. So let me give you an example. Like you have the production rules of this form. S goes to AB, S goes to BC, S goes to, okay, sorry, this is A goes to BA and A goes to A. Then other rules that you have is B goes to CC, B goes to B. Also you have the rules of the forms. C goes to AB and also C goes to A. If you see all the, okay, if you see here all in the RHS we are having either two non-terminals or a single terminal. So this follows what property of the grammar we just now discussed on the previous slide.
Chomsky normal form.
Yes. So all the productions are in the Chomsky normal form. Okay. But it is given, let's say we are to derive this string A, B. Okay. How can I derive this string? So I can use the production rules of the form S goes to A, B. Given, if you refer to the previous slide, I'm drawing it here. The parse tree can be drawn in this way. S goes to AB. A can give me A. We are to derive the string A, B. And then with B, we can get C, C. This is the production that is given here. B goes to C, C. Then C, you see here, it goes to AB as well as A. So we can put it once this way and we can also put it like this. A, B. And A can give me capital A because I have to derive the terminal string terminals in this string, so I will replace it with this production. A goes to A and B goes to B. So now here I am able to get this string. A goes to AAB. Okay. And yet another production can be of the form, if you see, S also leads to BC. Okay. So I will use this production BC, and then B can also give me CC. Right? So I will use C, this production rules, and C can give me A. And my goal is to derive this string, no? So I will refer to those productions which help me reach my goal, which help me reach to my desired string. Here I will replace C with capital A and B. So with capital A also I can get small a, terminal A. And with B I can get, so if I use this here, this will be a wrong one if I use this production here. Why? Because if I use B here, then I will be getting B. But my goal is to get the string A, B. So I will not be using this one. Let me erase it. So C can give me A. C can also give me B. Remove this one. And here C can give me A, B. This will not be B, this will be A. And A can give me A, and capital B gives me small b. So if you see here, just a second. So if you see here, to derive the same string A, I have two different parse trees. So whatever the structure that I have drawn, the sequence rules or the production rules that I use to derive my desired string, these are referred to as the parse trees. And here we can see for this one string A, I am having two parse trees. This is the first parse tree. This is the second parse tree. And we saw that the grammar is ambiguous if we have more than one derivation tree or a parse tree. Why we are calling it as derivation? Because it helps me to derive this string. Okay, so if we are having more than one derivation string, and we saw all the production rules were following this Chomsky normal form, still it led me to the ambiguous case. So that's why I marked this, that this statement is false. Instead of marking it as incorrect, the answer should be this only, B. And then in the third statement, it says it requires 2n minus 1 distinct productions in CNF to generate a string W of length n. So let's say all my derivations are of this form. A goes to BC or A goes to A. So if I am to derive the string W of length n, okay. So what can I do? I can first use this production rules. This production rule, like replacing a given string with the two non-terminals, and because this is of the length n, it will go n minus 1 times. So n minus 1 times I will be using this production. And since I want to derive a particular string, so how many times I will be using this production given the length of the string is n, that is n. So in total, we can have n minus 1 plus n steps. That is 2n minus 1. But why still this statement is false? Why? Because it says the distinct production rules. These production rules need not be distinct. Why? Because we saw here like one production, though these are two different production, it helps me to derive the stream. So this distinct creates the problem here. This is fine that it requires 2n minus 1 production rules in CNF to generate the string of length n. But here this word distinct is wrong. So the correct answer would be for this question B and C. So I hope it is clear to everyone. Let me know in case you have any doubts. Here B is also the correct option only. B and C. These are the correct options. Okay. So any doubts, anyone? Please ask. Please try to join by 6 or 6:05 from next time onwards. It will help you to attend the entire discussion section and get your doubts resolved. So any doubts, please raise your hand if you have any doubt in this question. Okay, so moving on to the next question. Here it again, I already told you the concept of CNF, Chomsky normal form. I'll again discuss that concept. What does it require? CNF, that the rule should be of the form A goes to BC or A goes to A. That is, in the RHS, you should be having either two non-terminals or a single terminal. So in this production set that have been given to you, three rules here, you are to convert this into CNF. And the question asks how many non-terminals do you need to add to this grammar to convert it into Chomsky normal form. So please give it an attempt. I've already given you the hint here. This is your hint to solve this question. Please try to solve and report your answer in the chat box. Give it a try. If you have gone through the lectures, you will be able to attempt it. Please give it a try. Okay, give it a try once. We'll discuss it shortly. Put your answers in the chat box after you have solved it. Let us see how many people have been able to solve it. B. Many people are saying to option B. Okay. 1 minute more. This is an easy question. Okay, let us see how we can solve this. So here, the first issue that comes is in this production. You can break it down like this. I'll use the next slide. So here in the question we were given that S goes to capital A, small c, B, and C. D goes to C, A or epsilon, and A goes to capital B, C or B. So we can break this. Let's say this is your first production, this is the second, and this is the third one. So how can we break the first production? Is like S goes to A, S goes to CB, and S goes to C. So the issue comes here. Why? Because in the Chomsky normal form, we are required that all the production rules should be of this form. A goes to B, C, that is two non-terminals, or A goes to A, that is a single terminal. But here we are having the combination of a terminal and a non-terminal. That is not included in our rules. So we got to convert this. This is the first issue that arises. So how can we do this? We can use some another variable. Let's say we use x, and we can say that this x helps me to derive this c. Then what can I do? It becomes like s goes to cb, that is the original rule. But now this c I can replace with this x, so then this rule becomes like s goes to xb, where x goes to c. So still if you substitute, you will be able to get this original rule. So how many variables we added here is this one. This is the one variable that we have added, x goes to c, and now our new rule becomes like this. So this first production, it gets reduced to s goes to a, or it goes to xb, or it goes to c. Okay, so this is allowed or not? This is completely allowed. Why? Because we are having two non-terminals and we are having a single terminal. This is absolutely fine. So now the other problem arises here in the second production, where it says B goes to small c, capital A or epsilon. So here it will be like, again we will be using our original this rule that we kept here, no, x goes to c, that you can use here also. So it can become like this, you can replace with capital X, so it will become like XAA. So here you could be writing capital XAA or epsilon. But if you see, it is still not in the Chomsky normal form. Why? Because we are having three terminals here. We are having, three non-terminals we are having here. So what you could do, you could replace this XA with another symbol. Okay, so this can be like T goes to XA. Okay, and then this, using this, replacing this capital XA with this T, your new production can become of the form B goes to TA or epsilon. Okay, so this is the second production that you added to make this grammar in the Chomsky normal form, and your resultant rule becomes like B goes to T, capital T, A or epsilon. And in the third case, we were having the production of the form A goes to capital B, C or B. So here This C is creating a problem, and already we had the production of this form that we used on the previous slide, x goes to C. That you can again use here, and then this will become like A goes to B. You replace it with capital X, so it will become like BX or B. So it is again in the Chomsky normal form, BX or B. So your resultant grammar, how does it look like? It looks like B goes to TA or epsilon, A goes to B capital X or B, T goes to capital X or A, X goes to C, and what was our first production? S goes to A, X, B or C, A, X, B or C. So what all I added here is this production, this I added, these two I added, and these two are the non-terminals that I added. So the answer is going to be 2, that is option B. So your answer is option B.
Ma'am,
Yes,
I have one question.
yes.
When you are replacing the non-terminals, can we replace it with any pair of adjacent non-terminals? So, for example, when
Here,
in
no?
this derivative, yes. So
Yes.
we have B giving XAA, we replace T, we add a production rule, T giving XA. Can we have instead T giving AA as a production rule also?
Yes, yes, yes. That is absolutely allowed.
Okay.
Yeah.
But let's say, supposing we have it as XAB, okay,
Mm-hmm.
or XAC for that matter, capital C,
Mm-hmm.
which is say another non-terminal, we
Mm-hmm.
can't have a production rule as B giving XC,
No,
right?
no, no. So you,
Okay.
I think, just a second. So let me explain. So you are saying, let's say we have the production rule of XAC, right?
Yes,
And
ma'am.
you want to, let's say, replace XC with some T, right? And
Yes.
then you want to use that.
Yes.
No,
We
that is
can't use
not
that.
allowed. Now, this A will, how
Okay.
will you justify what you have done to this?
Okay.
That is not allowed.
Okay.
You can hear what you could do is either,
XA or AC.
yes, you could replace either XA or AC. So it could be like B goes to TC, where T could be XA, or
Yes.
it could
So
be
it
like B
so
goes,
both the non-terminals have to be adjacent basically.
yes, yes, yes.
Okay.
T
Thanks.
goes to AC. This all both are allowed, but this is not allowed. This is not
Okay.
allowed. Yeah, because why they have to be adjacent? Because when you will be constructing parse trees like this, how will you justify like with what you have replaced? If you wanted this thing now, then in that this case, A should have gone to, an epsilon symbol. Like a production of this kind should have existed in your case. Then it would
Okay.
be nullified. But I think there was no such production listed in the rules, so this will not be allowed. Okay.
Okay.
Okay. So any other doubts? CNF grammar cannot contain unit production also. Uh, it can contain unit production in case it is deriving the terminals. I think you are talking about this case where S goes to capital A, right? But I think this is allowed. Though it is not mentioned, these are, conversion rules of CFG to CNF. These are the conversion rules. I think because this is given in the grammar, it can be considered as allowed. Okay, Rajni. I think Rajni was the person who had the doubt. Is it clear? Okay, great. Moving on to the third question. Give this one a try. What is PCFG? Probabilistic context-free grammar. So it is same as your CFG, except the case that here your production rules will be having the probability values. That is the only difference. So A goes to BC. Okay. So consider this as different, like here maybe you could consider a line. Yeah, like wait. So this is one set of the production rules and this is another. So in all we have 1, 2, 3, 4, 5, 6, 7, 8 production rules are here and you are to derive the string AAAB. What is the probability of getting the string using these production rules? Give this question a try. This is a good question. I'll give you 5 to 7 minutes to solve this question. Give it a try. And please put your answers in the chat box. I would request everyone to give this question a try. This will help us to apply the concepts we have learned through the video lectures and help us to know whether we are understanding or not or to what extent we understand. So please give it a try. In case you have any doubt, please let me know. 0.8 and this you consider as 0.8 only. Okay. Give it a try once. All of you, please solve this question. This is your production rule and this is the probability of that production rule. Draw the parse trees and then you try to derive this string. And for every production you are using, you put these probabilities. You have to consider all the parse trees that you can use to solve this question. So your hint is use all parse trees that are possible to derive the given string. Please, everyone, give a try. Let us see if there are any answers in the chat box. Are you people solving or shall I discuss straight away? Please let me know. Okay, solve. I'll give you 5 more minutes. Give it a try. Okay. Okay, I am starting with the discussion. I cannot see any answers in the chat box. So if you remember, in the lectures, Sir has discussed that in order to derive a particular string given in the form of PCFG, what do we do? Is like, let's say S goes to A, B, and A goes to some string. This is just an example. And let's say this production that S goes to AB had some value, let's say 0.5. A goes to A was 0.25. And B goes to B was 0.15. So let's say I have to derive this string AB. What I can do is I will refer what productions all I used. Like here I used all these three. Na? S goes to A, B, A goes to A, and B goes to B. So to know like what is the probability for this PCFG using this parse tree, I'm getting this string. You will multiply the probabilities that of all the productions that you have used here. So you used all these three. So here what you can get is 0.5 into 0.25 for the second production rule that you use, and 0.15. And let's say like this you had another parse tree. For that also you will multiply the individual probabilities of the production rules. And let's say you had two parse trees. So first parse tree, and with the second parse tree you got some value. Let's say this amounts to something like 0.95 and this comes out to be 0.08. So you will add these two, and then you will get the total probability of your parse tree, of all the parse trees generating that particular string. Okay, so that concept we are going to use here. So here we will see this for the first parse tree. We have been given these production rules, so I will be referring these only. So, okay, just a second. So, first parse tree. So what we can use here is the production of the form S goes to A, B. That I will use first. S goes to A, B, and my goal is to derive the string A, B. And with A, I can get the production of the form A goes to A. We see that this production is given here. A goes to A. And with B, I can use this production. B goes to C, and C goes to AB, and then I will use the other. So B goes to C, then one C can give me A. We have been given this production here. C goes to A. And also we have been given the production C goes to AB. And then A goes to A and then B goes to B. That we will use here. That C goes to A, B. And A goes to A and B goes to B. So this is like the string that I have been able to derive using these production rules. So
Is the answer A? Sorry, is the answer A?
Yes.
Yeah.
Who is this?
Nitish. It's the answer A, right?
Yes, yes.
Yeah.
Great. Great. So what are productions we use here? S goes to AB. We used A goes to A, and we will not remove the redundant productions. Okay, like here we have used A goes to A and A goes to A twice. So we will count it twice. We cannot consider that it is redundant. So you will take in multiplication its probability only once. Okay. And the other production that you use here is B goes to CC. Then you use C goes to A. Also you use C goes to AB, and A goes to A and B goes to B. The corresponding probabilities for them have been mentioned as for A, S goes to AB, it's like 0.5. For this is 0.7. I'm just taking it from here, like all the values that have been given here. Okay, B goes to CC is 0.4. Then 0.8, 0.2 for C goes to AB, 0.7 for A goes to A. If you see here, A goes to A is 0.7 and B goes to B is 0.6. That value is 0.6. So for the first, using the first parse tree, what is the probability for getting all of this? You will multiply all of this, that is 0.5 into 0.7 into 0.4, 0.8, and 0.2, 0.7 again, and 0.6. This value comes out to be equals to 0.009408. Okay, this is for your first parse tree using this parse tree, and this you have to figure out how many parse trees can be possible to derive this string. That you have to practice with a couple of other questions. Okay, so I'll be discussing what can be the second parse tree that is possible for this to derive the string AAAB. Okay, other production that we can use is S goes to AB, where A goes to, if you see here, A goes to B, A again. A goes to B, A, and then B goes to B. And then B goes to what? We have seen that B goes to CC, and C can help me to derive A. So this is a valid production in our case and we can therefore use it. B goes to CC, C goes to A, C goes to A, and also that A goes to A here. Okay, that also you can use. A goes to A. So now also I'm able to derive my desired string. A goes to AAB. And what are the productions that I have used here again is S goes to AB, A goes to BA, this one, B goes to B, then B goes to CC, this one, A goes to A, this, then C goes to A twice, and you will consider it twice because this has helped me to derive this particular terminal. So I think these are all that we have used, and we'll put their corresponding probability values of the production rules from here. So this will be 0.5, 0.3, 0.4, 0.8, 0.8, 0.7, and 0.6. You can match them. C goes to A, 0.7, and then I think C goes to A was 0.8, no? 0.8, 0.8, C goes to A. I think there is some little mistake. Let me write it properly so that there is no confusion. So S goes to AB, the value will be 0.5, 0.3 for here, 0.4, 0.8. B goes to CC is 0.4. C goes to A is A goes to A is 0.7 and C goes to A is 0.8 and 0.8. Okay, and B goes to B is 0.6. That values you can put from there, and A goes to B is 0.3. This is correct. S goes to AB. Yeah, all of these are correct. And for this parse tree, if you want to derive the string A, B using this parse tree, how will you get the values? 0.5 into 0.3 into 0.6. Just the multiplication of the individual production rules that you have employed to generate the string using this parse tree. 0.4 into 0.7 into 0.8 into 0.8. This value comes out to be 0.016128. Okay, then there is another third parse tree that is possible for this, that is third parse tree to derive B. So it's like S goes to B, C, and B goes to C, C, and C goes to A, B. With C, I want to derive the string A, B. So C goes to A, that we can take. C goes to A, this production we can use. C goes to A, again A goes to A we can use. And B goes to B, this production we can use. B goes to B. So what all are the productions that we have used here? Can anyone tell me now? We have already gone through two parse trees. Can anyone tell? Please unmute and tell so that I can know how well you people are understanding, or all of us are on the same page or not. Please tell what are the production rules I have employed here. Please unmute and tell.
S goes to BC.
S goes to BC.
B goes to CC.
Yes.
C goes to AB.
C goes to AB. Yes, correct.
C goes to A.
Mm-hmm.
C goes to A again.
Mm-hmm.
A goes to A, B goes to B.
Yes. Now you will put the values for these respective production rules from this page. Okay. From the rules that have been given here. Okay, so what can be the values here? That for here will be 0.5, for here will be 0.4, please ignore this. This will be 0.8. For C goes to A is again 0.8. C goes to AB is 0.2. Okay. And C goes to A is again 0.8. A goes to A is 0.7 and B goes to B is 0.6. So the overall probability that I have to derive this string using this parse tree would be 0.5 into 0.4 into 0.2 into 0.8 into 0.8 into 0.7 into 0.6, and that value comes out to be 0.01710752. If you remember, the concept that I told you here in this slide is like we have to, in order to know what is the possible, what is the collective probability with which I can obtain this string using the different parse trees, I will add the values that I have obtained from the different parse trees. So from the first parse tree, I obtained this particular value, this value 0.009408. Using the second parse tree, I obtained this value. And using the third parse tree, I obtained this value. Okay, so the overall probability would be like you will add, overall probability would be like you will add the probability that you have obtained from the first parse tree, from the second parse tree, and from the third parse tree. That value would be 0.009408 plus 0.016128 plus 0.010752. This values, if you add, it will come out to be equals to 3.636 into 10 power minus 2. That is contained in your option A. So the answer is going to be option. So this is the, please go through this once and just let me know in case you have any doubts. Please put, so please go through this. I hope you will be able to solve the questions like this now. Anybody having any doubt? The only thing that you have to figure out here is like what are the possible strings that you can draw to obtain, what are the possible parse trees that you can use to obtain the given string. Okay, that is the only challenge in this question that you have to figure out. To derive this particular string AAAB, in our case we had three parse trees. We draw how we could, we used all the production rules. Am I audible? Okay.
Yes, ma'am.
Yeah. So in our case, we first figured out like there are the three parse trees. Using these given production rules to obtain this desired string, we just put the production rules that are valid in our case, take the probabilities for those respective production rules, and get the probability of deriving the string using a particular parse tree. Here we did it for three different parse trees, and in the end, to obtain the overall probability for generating the string using the entire set of the given production rules, we add the probabilities that we have obtained using the three parse trees individually, and whatever is the resultant is the probability of getting the string using the given production rules. So any doubts, anybody? Please let me know. Sorry, Siddharth, the answer will be option A. Please check your solution with the one that I discussed just now. Please see the where you might have made a mistake. I hope it is clear to everyone. So these kind of questions are likely to come in the exam. So, and these are easy as well. So you can give it a try once. Let me know in case anybody has any doubt. Anybody any doubt? Siddharth, let me know, Siddharth, what is the doubt? Please tell. Okay, I think we are about to reach the end of session today, though there were some more questions that I would have discussed. But given the time constraint, maybe you can solve them in your next lectures. In today's lecture, if you have any doubt, please let me know. This is the concept that we use for this question, and this is the detailed solution. Okay, then I am closing. We are about to reach the time. Anybody, any doubts? Okay, great. I hope everything is clear. Yes, Ketan, please tell. I left the meeting. Okay. Okay, then thank you all for attending today's session. I hope these sessions are useful for you to solve your assignments. Please try to solve the questions because the questions that are being given to you in the current run are more or less related to these questions that we discuss in the live sessions. So I would encourage all to please go through the lectures first before coming for the live sessions. It will help you to obtain better understanding of the concepts. Do write back to me in case you have any doubts in any of the sessions that I have covered so far. You can reach out to me at this is my YouTube channel link where I upload all the videos for the live sessions that I am discussing. And this is my email address in case you